Okay, welcome back. Today we are talking about linear equations in lecture 4. All right, so moving on, just another type of equation and another technique to solve them. So next we solve linear equations using something very fancy sounding, using something called an integrating factor, which I will abbreviate as IF pretty often because I don't want to keep writing it. The idea is very simple, very clever and simple. So let's compare it to something we know about. So like in algebra, you might solve something like 1 over x minus 3 equals 2x. By doing what? Well, you have to multiply by the same thing on both sides. And doing so doesn't actually change the equation, just writes it in a different form, in a more helpful form. So that's the idea with integrating factors. You make your differential equation easier by multiplying by something. So here we multiply by something called an integrating factor to make the differential equation doable. Same idea, except it looks a bit more complicated. Okay, so we got to do this for linear equations. So what is a linear equation? So given a linear equation, i.e. one that can, again, doesn't have to start like this, be written as, so a linear equation is one that can be written as y prime plus some function of x. So there's just a bunch of stuff with x. So it could be like sine of x, cosine of x, x cubed, stuff like that, times y. And then on the other side is other functions of x. So stuff with x on that side too. So if you have an equation that's in this form, then the claim is if you multiply both sides by this very strange looking thing, e to the power of the integral of p of x, meaning the same p of x, whatever's here, that's what you're integrating there. If you multiply by this big thing, then it's doable. Then you can do the integral. Then you can, solve the differential equation to solve the DE. Okay, so what we're going to do is we're going to run through it with an example and then do it in general and see why it's working. So right now it seems a bit like magic. You just have this differential equation of this form, and then seemingly by magic, if I multiply by this guy, I'll be able to do it, apparently. Well, let's see. This happens a lot in this class. We learn techniques, and they seem like magic until later when we see where they come from. But right now, we just want to focus on doing techniques. Okay, so here is a linear equation. So it's in the right form. So what's p of x? P of x is 1 over x. It's being multiplied to the y variable. And q of x is the function of x on the other side. So it's that. Okay, so it's linear. So now let's think about this integrating factor, is what it's called. So I'm supposed to do e to the integral of p of x. So that would be e to the integral of 1 over x. So I know the integral of 1 over x, luckily. It's ln of x. And then I'm going to add c here, just because that's what you're used to doing. But later we'll see we don't actually need that. And then I can simplify this because it's e to the ln of x times e to the c. So this becomes x times a constant. So then I'm just going to rename that constant to be c again. Okay. So this is the integrating factor. Once it's all said and done, and I've calculated it, it's c times x, a constant times x. So apparently, if I multiply that, because that's what this is in this situation, if I multiply it to the original linear equation, I will be able to solve it. So let's do that. Okay, so now multiply. So cx times y prime plus 1 over x y equals cx times, what was q of x? It was just x. Okay, so I've multiplied c times x to both sides. And now let's see, how does this help? Apparently it's supposed to help. It doesn't look any easier as to solve. Well, what if I distribute? So let's do that. Okay, I guess something looks a little bit easier because I can cancel x over x. But it really doesn't seem any easier. Yeah, how does this suddenly become a differential equation I can solve? It's not separable. It's not homogeneous, I don't think. So I can't use that stuff I did last time. So this is where I have to reveal the illusion. I have to pull back the curtain and show you why it is actually easier. So it doesn't look easier at first glance. But the left side is actually something we can work with. It can be rewritten if you just remember, you go back in time and remember a little bit of calculus. So here's the claim. It's actually, the left side is the result of the product rule on something. So what's the product rule? The product rule says if I take the derivative of two functions being multiplied together, then I just have to take the derivative of one, keep the second one the same, and then do the opposite. Keep the first one the same and then take the derivative of the second. So somehow this is actually coming from the product rule of something. But it's very hard to see until I just do it. So I just have to give it away and just tell you where it's coming from. So it's actually the derivative of y times our integrating factor. So notice that this is the integrating factor, and that will always happen actually with this technique. So let's take the derivative of y times our integrating factor using the product rule. So the product rule says take the derivative of the first thing, keep the second one the same, add, keep the first one the same, take the derivative of the second thing. Okay, so what's the derivative of y with respect to x? Well, y is a function of x, so it's just y prime. Then I keep cx the same, keep y the same. Now I take the derivative of a constant times x. That's just that constant. And it's very similar to this, except, going way back in time. Whoopsie, what did I do wrong up here? I forgot this constant, I just left it behind. Whoops. Okay, that'll fix everything. That constant should be there, should also be there. And now it's what I wanted. Okay, so now isn't this thing the same as this thing? It is. I just rewrote it a little bit differently because I got it from the product rule. So let's just fix it up so it looks the same. And voila, it is the same. So what does that mean? So at the step that we have right now, so what we currently have is we have cx y prime plus cy, oops, forgot the c again, equals cx squared. We currently have that. And what I'm claiming is that this left side is actually the result of doing the derivative of y times cx. So I'm just going to replace the left side with this thing. So this becomes, the left side is actually just the derivative of y times cx. Now, why is this is the most important step? Why is this such a good step? Well, because now on the right side, one thing we should notice is it's only a function of x. And on the left side, I have a derivative with respect to x. So what I can do to continue is I can integrate with respect to x on both sides. And what will that do for me? Well, on the right side, I'll just be able to do the integral because it's a function of x, so I can just do that. But on the left side, I have to remember that integrals and derivatives are sort of opposites of each other. They undo each other. And that comes from the fundamental theorem of calculus, which I'm not going to review that whole thing because all I need it for right now is to say that on the left side, we can think of the derivative and the integral as sort of canceling. And you can make this precise, but we're not going to. Not enough payoff. So we're just going to think of it as canceling. And what we're left with is just y times cx. So the integral and the derivative are sort of canceling out, and all I'm left with is y times cx. And then on the right side, I can just do the integral. So that becomes cx cubed over 3 plus, I guess I need another name for a constant, d. And now I've solved the differential equation because I've found my function of x, or my relation, but in this case it is a function. If I just divide by cx now and everything, notice that those c's cancel. So I just get x squared over 3. And then d over c is just some constant, so I'm going to rename it to make it look nicer. I'm just going to call it c again. That was 1 over x. So this is a one parameter family of solutions. And it's an explicit solution because I've solved for y. So of course, you could check that the technique actually worked by taking the derivative, plugging it back into the original differential equation way up here, way up here, and seeing that it works out. But it will, and let's see why by thinking about why this will always work by thinking about the general case. So this was just one specific example of using this technique. Okay, so let's see why this always works. Okay, so we're just going to think about, so I know this is not a proof class, but this is sort of like a proof. So we're just going to think about a general linear equation. So we're not picking specific p of x or q of x. And then we're just going to multiply by the integrating factor that we claim will always make this work out, e to the integral of p of x dx. Okay, so let's multiply by it. So I get e to the integral p of x dx times y prime plus p of x times e to the integral of p of x dx times y equals e to the integral p of x dx times q of x. Okay. So the idea is that on the left side, it's supposed to be the product rule of something. And here we can actually see it a little bit better. So if I look at it carefully, so I should think of it in these two pieces. I have my one function, that would be like my f, and then my other function, g. And the product rule says that when I take the derivative, I should, so I've done it a bit backwards, so let me rename them to make it look the same here. So let's call this one f and this one g. So the product rule says, okay, if I want to take the derivative of the multiplication of two functions, I have to do the derivative of one times the other plus the derivative of the other one times the other. You can write it in different orders, it works out the same. But in any case, that's exactly what's going on. So here I have f prime times g. I just wrote it backwards because y is f. And then this better be g prime for everything to work out. And it will. So let's actually calculate this. Okay, so let's do that. So if I take the derivative of y times my integrating factor, then let's see that it will turn out to always be this left side. Okay, so the chain rule, the product rule says derivative of the first, keep the second one the same. And already we can see that, yes, that is going to be this piece there, because d dx of y is just y prime. And all I did was write it multiplied the other way, but it's the same thing. So maybe I'll just rewrite it to match the other order. Okay, but then to finish the product rule, I have to add and I have to leave y alone and take the derivative of the second function, which would be my integrating factor. And how do I do that? Well, what's the derivative of e to the something? Well, the rule is it's e to that same something. You don't change it at all. The derivative of e to the something is e to the something times, and then the chain rule says I have to take the derivative of that something, whatever is inside of the e. So this is coming from the chain rule here. But then I can actually calculate this because same idea as before, that derivative and the integral are canceling, and I'm just left with p of x there. So this becomes y times e to the integral p of x dx times p of x. But isn't that what I have way up here? Isn't that this, just written in a different order? It is. It's the same thing. I just put the p of x somewhere else, so maybe I'll reorder it till it looks exactly the same. But that's not totally necessary. I can't remember which order did I put it in. Okay, p of x e to the integral p of x dx times y. Okay, so what this is saying is, in my differential equation, I started here, I multiplied by this thing, and now I'm here. But the left side I can replace with just the derivative of y times the integrating factor, because what I've done is I've shown that that's exactly what the left side is. The left side is this, but it's actually this. Okay, so then this becomes d over dx times of y times the integrating factor on the left side. The whole left side just becomes that. The right side, we didn't do anything, so it's just what we had before. So it's the integrating factor times q to the q of x. So because we're doing this in a general form, this is actually telling us what we could do in general. We could actually plug things in and use this as a formula. But I recommend doing the steps each time. So in any case, the rest of the steps are not as difficult to grasp. All we do is integrate both sides with respect to x. And the point of that is that on the left side, the integral and the derivative will vanish together. And on the right, I'll just have to manually calculate whatever this is. And it can get very complicated, or it can be impossible to actually do. And then I can solve for y by just dividing. And doing so gives us an actual complete formula for the solution. If you go all the way back to the start and you just plug p of x and q of x into this guy and calculate this, this will actually give you the solution to the linear equation. But it's better to go through the process just to practice the process. So let's do it that way. Let's not use this as a formula. This is just showing you that the process will always end up with a solution. Okay, so let's see how many more examples I can fit in before I run out of energy. Oops, let's change that to a 6. So this example is to show to you, to remind you that functions of x don't always have to have an x in them, but they still count as functions of x. So first identify this as linear. Do you see why it's linear? Well, if I divide by the 2, now it's in the form that reveals that it's linear. You might think, well, there's no x's though. That's okay. This is a perfectly fine function of x. It's called a constant function, where no matter what x you plug in, you get -3 as your answer. This is a perfectly fine function of x called 6, which when you plug things in, 6 pops out, no matter what. Still counts as a function of x, so this is in fact linear. Great. So now to continue, I just need the integrating factor. So I don't know why I started numbering my steps, but maybe it'll make things more clear. So let's do that. So now I'll get the integrating factor, and it's always e to the integral of p of x dx. So e to the integral of -3 dx, which is e to the -3x. Now, note, I'm not going to put a plus c like I did last time. The reason being is that I'm not integrating something to solve the equation. I'm integrating something to get something to multiply to make things easier. And it doesn't actually matter what constant you put here, the trick will work. So multiplying by this will work for any c, doesn't matter which c you use, and it's not part of the solution. So let's just use c equals 0 to save time when we multiply. Okay, so now let's multiply. And you can check for yourself that this c doesn't matter by keeping it there and carrying it through and seeing what it does to the solution at the end. Okay, so I'm multiplying by this integrating factor to my differential equation. Oops. So I multiplied e to the negative 3x to both sides, and then I also distributed just to skip a step. And now what I'm doing is I'm changing the left side because of the product rule. This left side is secretly in reverse the derivative of y times the integrating factor. So once again, this is just the integrating factor. So you don't have to prove it each time because we proved it in general. It'll always be y times the integrating factor. If I take this derivative, I do the product rule, it'll become this guy again. And so all I'm doing is replacing it with the derivative of these two things multiplied together. So that step will always be the same. So once you get really used to it, you can really very quickly skip a couple steps because the next step is to integrate. And you already know that the point of integrating on the left side is that it'll cancel that derivative. So very quickly, I could just skip all the way to this step. Once I've seen the pattern. Okay, so now we'll just continue to calculate the integral. So the integral of 6e to the negative 3x is 6e to the negative 3x over negative 3. You can use u substitution to check that if you like. And then I can make this an explicit solution very easily, so I will, just by dividing by e to the negative 3x. Oops. And I can simplify pretty well, so I'll do that. Negative 2 plus ce to the 3x. Negative power flips it back over. Okay, so this is my one parameter family of solutions I get by using this technique on the linear differential equation. Okay, let's see. I guess I'll do one more. Here are two good ones. I'll just do one, but I'll write both of them down if you want to practice on your own. And here's another one. Let's see, I guess I'll do the second one because it looks easier. Okay, or maybe I'll set them both up and then you can finish them. So I'll call this one, call that 2. So for 1, p of x is x squared. So my integrating factor is e to the integral of x squared dx, which becomes e to the x cubed over 3. And then for 2, my p of x is negative 7, which tells me my integrating factor will be e to the integral negative 7. That looks terrible. Let me write that. Negative 7 dx, which is e to the negative 7x. So those are my two integrating factors. On the first one, so because we know that there's a pattern, we already know that after I multiply it, what am I going to do? Then I'm going to rewrite it using the product rule. And it's always just going to become d dx of y times the integrating factor. So you can do those steps again if you want, but it's always going to be the derivative of y times the integrating factor on the left. And then on the right, I have to actually multiply my q of x, whatever's over there, times the integrating factor. So this one's going to be e to the x cubed over 3 times x squared. And then the next one is going to be e to the negative 7x times e to the x, because e to the x is my q of x. And then I'm going to integrate both sides. And I already know that the integral and the derivative will cancel on the left, so I'm just gonna immediately write it like this in both cases. But then on the right, I have to actually do the integral. So that's the hard part of this technique is, can I do this integral? And if I can't, then this is where I would get stuck. So on the first one, I can use u sub. If you just do u equals x cubed over 3, it'll work out. And on this one, well, you have to remember that you can add the powers because the bases are the same. So this is really just e to the negative 6x, because negative 7 plus 1x gives you negative 6x's. And then that integral you can do very quickly with u sub as well, but it's going to be e to the negative 6x divided by negative 6 plus c. And then that will finish it off. Let's see. Just by dividing by that e to the negative 7x. So what does that become? That just becomes negative e to the x over 6, because I just subtracted the powers. So you'll get negative 1x on the bottom, which flips over to e to the x. And this is just e to the 7x times a constant. So that's the end of that one. I will leave it to you to finish this one. You just have to use u sub to integrate and then divide again. It's the same thing. Okay. So I just want to say a couple things. So for now, this technique seems a bit like a magic trick. I just told you, do this and it'll work. And then it did work. But why would you think to do that in the first place? So that's what we'll have to figure out later. So later, two things. We'll see why one might come up with this integrating factor technique. Meaning, why would you think to, okay, I have this differential equation, I'll just multiply by this thing and suddenly it'll work. Why would you think to do that? So right now it's a complete mystery. And then the other interesting thing that we'll reveal is that the one parameter family that we get by doing this actually consists of all the solutions. Meaning there's no hidden solutions. All the solutions are of that form for that differential equation. And this was a question from, I think last time or a couple times ago, which is like, okay, I gave you a technique. How do you know that that gives you all the solutions? What if there's other ones that come from different techniques? So it turns out for this technique, this does give you all the solutions, but we'll see why much later. Okay, so that's it for today. See you next time.